Welcome everybody, I'm Tyron Erasmus, and today I'm going to be talking about a talk entitled The Heavy Metal That Poisoned the Droid, and you'll soon find out why it's actually called that. So we're just going to be going over a brief introduction of the Android security model, and then weighing up various types of analysis that you can do on Android devices and Android applications using static and dynamic analysis. And then we're going to go through something that I've been developing, a new framework called Mercury to do exactly this. And then just looking at various OEM problems and techniques that malware could possibly use. So I'm a consultant at MWR InfoSecurity, the South African office, and 25% of my time is spent on research. Over the past couple of months, I have done research specifically on Android, but I'm also interested in various areas of exploitation as well. So why Android? Well, to be honest, I'm a bit of an Android fanboy, so maybe that's number one reason. But also, it's got very interesting attack surfaces. There's quite a lot of attack surface in the way that applications communicate with each other across the sandbox using IPC. Also, because it's good old Linux, so there's always the chance of priv-esking up to root, which any security researcher enjoys. So if we look at a brief overview of the security model, each application on a device runs in the context of its own user, so it gets its own UID and GID, and it essentially it actually uses a Unix sandboxing method rather than anything else. That's what it predominantly relies on, which is obviously different from conventional computing, where any application that you start runs in the context of the user that opened it. There is an exception to this case where shared UIDs are used, but I'm not going to go too much into that. So this basically provides application resource isolation from a point of view of different applications. So an example of this is if you actually run PS on an Android device, you'll see there that the user column on the left, each application runs as a different user. You'll see down there there's App 8, App 4, App 7. So each application actually gets its own little area of the file system that it can write its own private data files and various things into. And it actually uses Unix because they're running as separate users. If application 1 tries to access application 2's data, it'll be explicitly denied, obviously because of the Unix permissions set. Now there is an exception to this as well. You're also able to write files to your own private data area with the world readable flag on, which is obviously would be a direct security breach, because then application 1 could effectively read application 2's data. So from an application manifest point of view, each application comes with something called Android manifest.xml, and this defines all your configuration parameters and your security parameters when you're looking at communicating across the sandbox. It's got quite a specialized IPC mechanism on Android, and we'll be looking into that as well. There also exists the possibility for memory corruption vulnerabilities. You're actually able to run native code that can obviously be overflowed on an Android device. And there are some restrictions that apply to this, though. If you actually get code execution from overflowing a native component, you are exploiting an app, you'll gain the privileges of the application that you exploit. And basically the only way there to actually gain more privileges is you versus the kernel. So if you look at the IPC, applications can actually communicate with each other across this sandbox using inter-process communication. And it's a very well-defined structure for these communications. And basically how it's done is, in that Android manifest.xml file, you actually explicitly state which endpoints you would actually like to export or not. There are some things that are tricky about this that developers often overlook, which we'll look into as well. So looking at the 4 different types of IPC endpoints that you actually get, There's activities, which is just your typical visual element of an application. When you open an application, that's basically what you see. Services, which are your background workers, don't provide a user interface and can perform long-running tasks. What's interesting as well, which is in relation to the native code, is that often services actually provide input or accept input that they feed into native components via services. So you can possibly bind to a service and overflow one of the native components in another application and gain the privileges of that application. Then broadcast receivers. So this is the part of Android that sort of gives it its event-driven nature. So you can register for a broadcast. Hey, I want to receive notifications about new SMSs coming in, or there's loads of different notifications. Has the screen just been turned off, or a whole range of different notifications. And then content providers, which I'm particularly interested in, is your typical data storehouse for an application. It feels very much like SQL. So the methods that are actually provided across the sandbox are your typical query, insert, delete, things that are very familiar to anyone who's played with SQL a bit. And so the bottom line is that all 4 of these RPC endpoints can actually be exported to other applications, and this can be done in one of 2 ways. It can be explicitly exported in the Android manifest file of an application, so you can set a flag there, exported equals true, and then other applications can actually interact with that component. Or implicitly, also via something called an intent filter, which I also won't go much into. Something that catches a lot of developers out, if you just download, say, the top 20 applications on the Android marketplace, is that content providers are actually exported by default. So if you don't have an exported equals false or something like that, then basically your content provider is being exported to other applications on the same device. So if we look at something simple, like, so this is a typical situation. You have some simple application, maybe it only has one activity, but it's often the case that through the IPC mechanisms there, so through the little Android in the middle, it can read the content provider of another application without any extra permissions whatsoever. And this goes for the same for if it has an exported activity, it'll be able to start that. If it has an exported service, you could possibly start the service or bind to it. And there's also a lot of interesting attacks with the code that services actually export to other applications. So if you look at what the media and the typical security auditor will tell you is always look at the permissions that the application is asking you. Look at the developer name. Does that ring true? Obviously, something like that raises questions. Why does a game need to send SMSs? It's most probably malware. Some scary contradictions to that commonly given advice is applications that contain root exploits. So we've seen a couple of strains of malware actually implementing root exploits. I'm sure, yeah, you guys attended Dan's talk as well. We went through a couple of those. And then browser vulnerabilities. Android uses WebKit. There's loads of WebKit vulnerabilities found each year that you can use to exploit the phone, which I'll get into later as well. And then basically my area of research, which is cross-application exploitation. So what can one application do to another application without any privileges whatsoever? Yeah, so there I'm just saying again, from a completely unprivileged context, what kind of information can you steal from the device? What kind of services can you start? Or how can you have a negative impact on the other applications from within a sandboxed environment? And this has huge implications for malware, because your typical malware literally asks you for the permissions to do its evil task. Whereas if you can find vulnerabilities in other applications, all you basically need is possibly the internet permission. And this is so that if it steals data or something, that it can pipe it back to your server. Some guys have even found some methods of bypassing the internet permission as well. I'm also looking into a couple of methods at the moment for that. And as I mentioned, there's a very huge Android-specific attack surface. Android's very unique. Developers have not, in my opinion, got a full grasp on it yet. So there's a lot of common issues that arise, and it's ripe pickings at the moment for Android, for anyone looking for vulnerabilities. So if you look at your typical methods of actually examining or auditing a device or a specific application, it typically involves these steps. So there's a bunch of white papers on these type of methods. You basically start out by downloading the apps that you are interested in. You can use ADB, or you can use custom Python scripts to interact with tools from the Android SDK to be able to do this. And then there's various methods of decompiling this. It's Dalvik bytecode, which can basically be transformed into a jar file, which you can actually then just read the source code on it, or something that resembles the source code. Or, in some cases, you can't actually get the full view of the source code, but you can at least get a bytecode representation of the executable. Then you would take an application and also use a tool that comes with the Android SDK called AAPT, and you can actually extract the manifest file of the application. Then at this point, you're at a point where you can examine the attack vectors on an application. So you look at the manifest file and you say, okay, what are the entry points into this application? And then you look at the decompiled code and say, okay, behind these entry points, there's this code running. And from there, you can, well, that's the next step, is understanding the entry points, understanding potential flaws in the entry points, and then basically just writing some custom proof of concept code to try and exploit this. Now, this can actually be a very tedious process on complex applications. It's basically a big iterative loop of creating code, compiling, uploading, testing, analyzing what went wrong with your piece of code, then amending. It's a huge iterative process, and it's actually very time-consuming. All the applications need to be compiled and stuff obviously for Android, so you'd make a specific little app that does one test case for something. It actually becomes very cumbersome if you're reviewing a lot of apps, especially if you're reviewing a device. Then you've got maybe 100 apps to look at, and you've got to do this for all of them. It becomes a bit crazy. So if we look at a dynamic analysis approach to this, rather, why not have something that sits on the device that you can then identify attack vectors on the fly, get relevant information about them, and attempt to exploit them in line. So that cuts out a lot of the time needed to analyze an application. So yeah, it's very time efficient. I believe you can gain much better coverage of a device if you're able to do things quicker. And why not even create some reusable modules? I mean, there's common issues that arise across applications, so why not just create a module to look for something specific in a range of applications, as opposed to doing it manually on each one of those apps. So that's where my research comes in. A new tool, well, framework, called Mercury, and which is the heavy metal that poisons the Droid. So if we look at what is it, it's a platform for effective vulnerability hunting. Instead of using a collection of custom Python scripts or little apps, you could make use of a single console that incorporates a selection of tools. And also, it's very modular. You can write your own module for it. It was actually designed for extension. So if you think that there's something cool that you want to do that's not already included in the framework, just add a module, and yeah. So a lot of the modules included already with Mercury allow a fair amount of automation with regards to looking for these types of issues on a device. And it uses an interface that's very familiar to pen testers, which we'll see now. So as I mentioned, the reason for its existence is it's a framework versus custom scripts. That's basically what it comes down to. If you look at other frameworks, well, before something like Metasploit became commonplace, it was just a collection of little Perl scripts and things like that you ran. There was no real structure to being able to find relevant vulnerabilities or relevant exploits for the vulnerabilities that you found. And one interesting thing about Mercury is that it only has one installation permission, which is the internet permission. And the only reason that it has this is to be able to communicate with its client. So I'll go into the server-client model that it uses as well. And it's also got big implications, because if you can find if you can exploit an application across a sandbox using Mercury, then malware can do it too. And the only permission that you're required to do this is the internet permission. And then also just to create a place where the community can share proof of concept exploits, new modules, new ways to analyze apps. Maybe there's something new that they add to Android, just add a module for Mercury and to the benefits of the community. So if we look at how it works, it uses a client-server model. So the server actually runs on the Android device. It basically just exposes a port, which then you can connect to from the client. The client was actually, it's a framework written in Python, which is very extendable and very modular as well. So I'm hoping to see some cool contributions to it. Okay, so enough of the talk. Let's actually get down to using it. Okay, so this is basically how it looks when you start it up. And I actually have a device connected via USB at the moment. It doesn't actually need to be connected over USB. It can be connected over a wireless LAN as well. I just had a couple of nightmares about people in the audience de-authing me though on the wireless. I decided against that. Cool. So we connected, and you see the 4 IPC endpoints are present here. There's activities, broadcast receivers, services, and content providers, and then various other sections that allow you to look at various aspects of a device or an application. So if we look at something which is typically done by custom Python scripts, is guys write scripts to download all the packages on a device, or they just want to basically look at, extract all the manifests so that they can observe the endpoints. But why do that when you can just do something like type info and everything pops up here? If you look at an application here, it gives you the package name, its APK path. Yeah, it even tells you that there's a shared user ID, which has various security implications as well. And then the permissions that were assigned to it, well, granted to it when installing it. So you can do some interesting things as well. Like if we look at, let's just type help info, yeah. So there's various filters that you can put in this as well. So you can say, okay, I'm only looking for information about this package, or information that contains these permissions. So an interesting filter to put on here is, I know that many bug hunters in the audience will definitely be looking at packages that have the install packages permission. Those obviously have the biggest implications, because if you can exploit one of these applications, feed it your APK file with whatever permissions you choose, and get it to install it, obviously that's a direct win on Android. That's basically the equivalent of having root access, but not quite on a Linux level. Another interesting thing here, so let's actually look at an application that has the install packages permission, like this. Okay, and then there's a command called attack surface. So there we go, we see that this has got an activity, which is obviously just its main activity, 4 broadcast receivers exported, and you see that it has a shared user ID. So it would be interesting to see what other applications have the same user ID. Maybe you could attack this application via another application that shares its user ID. Just interesting filters that you can put on things to find information that's relevant to what you're actually trying to achieve. And then if we look at something else, something that's very interesting is content providers. Okay, so we can type info here, and it'll give us a whole list of all the content providers on the device. And a very interesting thing to note here is that a load of these content providers don't require any permissions whatsoever to read from or write to. You'll see something like your contact or your call log will require the read contacts to be able to read from the content provider and write contacts to write to it. But it's also the case where there's a lot that don't actually require anything. So that obviously has quite a lot of implications for malware. It also includes two different types of shells. So there's one-off shell, which basically just you give it a command, it executes it, returns, and gives you the result. It doesn't actually keep its state. Whereas, yeah, so we can type ls here. You can see I got busybox there. Or you could use a persistent shell, which actually makes use of a native component to open a file descriptor to a shell and interact with it that way. So it's just two different types of shells. So interesting fact number one is that any application can actually see verbose system information regardless of the permissions assigned to it. So any application can see all the installed applications, platform and device specifics. I'll get into that later. And most times the identity of the phone. So in my research I've seen that you can get the IMEI number, the IMSI number, the phone number pretty much without any permissions. And the impact of this is that someone could profile your device. So let's say it lists all the installed applications, phones home, and says, okay, do we have any available exploits for these vulnerable apps? And then actually, targets them and performs an undesired action. The fact that an application can get device information allows for better targeting of root exploits. So you could have a piece of malware on the marketplace that all it is just a shell. It profiles your device, phones home, and says, okay, do we have a root exploit or any kind of exploits for these vulnerable apps? And it could then download a root exploit, execute it, and get a root shell on your phone. Or someone could use this information to track you. So if you look at something like the Common San Diego project, which was presented last year, I think, in America somewhere, this information is very relevant for the tracking of someone. And again, the only permission needed to perform any of these attacks is the internet permission. So interesting fact number two is that any application on your device, regardless of their permissions, can actually read the contents of your SD card. Now, that might not be news to some people, but I think it will definitely be news to a lot of developers. They place a lot of things on the SD card that they think that you need the permissions, any permissions to read from. So let's actually have a look at that in Mercury. I'm just going to go into the one-off shell. So we'll see here, and the reason why you can actually read the contents of the SD card, I'm talking about internal and external SD card here, is the fact that the global read is assigned to all files and folders written to the SD card. I believe it's got to do with the way, maybe, FAT, exactly, yeah. Okay, yeah, and exactly, the reason is it's the law of the Unix verse. Okay, so some of the implications of this is that a malicious application could upload the contents of your SD card to the internet. That's quite an uncomfortable thought. If you think about photos, videos, documents, if you read any sensitive documents on your phone, or anything else that's interesting on your SD card. So yeah, the only permission required is obviously the internet permission, or if you can find some other sneaky technique of feeding it through the browser. I've seen a guy do that before as well. Then another really interesting feature of Android is that while you're developing an application, your application starts out as being debuggable, okay? And at the point where you release it to the marketplace, if you don't actually set debuggable equal to false, then it's actually possible for a malicious application to say to your debuggable application, hey, I'm the debugger. How about executing this class of code? How about anything? You can basically broker a connection as a debugger from an unprivileged application, which is quite scary. We're working on we've got a proof of concept for that, and that's actually going to make its way into Mercury within the next couple of weeks for the community to have a bit of a play. And how it actually does this is it opens a socket called JDWP control. And by opening that socket, we found that you could actually, from an unprivileged context, open that socket, and then debuggable applications connect to you. And you can say, okay, yes, I'm your debugger, and do this, do that, anything that the debugger could actually do. Now, it's quite a complicated protocol given, but that's basically just a bit of obscurity, a bit of time spent to actually give it full debugging features. So one of the biggest things about Mercury is that it's actually extendable. So it will remove the need for writing custom little apps. There's always the case when you're looking at an application like, oh, I just want to try this one thing, and you have to write a whole Android app from scratch just to test that one thing. You've got no debugging structure on it whatsoever. So it's just an overall tedious experience. Also, as I've mentioned, you can share exploit proof of concepts. We've got it up on GitHub. I'll give the address later on in the presentation. So yeah, as a bit of a community effort, because I'm not claiming to say that I've put everything in this framework that needs to be there. Obviously, the security community has a lot to add to that. And some cool modules that we've already whipped up for Mercury is various pieces of information gathering tools, and your classic netcat shell. It's actually quite interesting. I'll show later. It's very old school and fairly obvious, but it's still cool to see a shell every once in a while. And then actually vulnerabilities that I found that allow the information pilfering of applications. There's some modules included as well. So if we look at Dropbox, I actually last year, July, found a vulnerability in Dropbox. I'm not sure if everyone's aware of what Dropbox is. So when I was actually writing, the whole idea for Mercury came along when I was busy writing the Dropbox proof of concept exploit. Okay, it was really tedious. If you look at all the values here that are actually in this little proof of concept exploit, I basically had to write a little application. It didn't work. I didn't know why either. There was no debugging structure in it. And basically what this proof of concept exploit was able to do is, because Dropbox had an exported content provider, I was able to inject into that content provider from another application, which you see there is called Dropbox, and then invoke a service. And what this would actually do is force Dropbox to upload its own username and password database into its public folder. So, and we all know that the public folder on Dropbox is internet accessible. So if we look at OEM applications, there's a lot of applications that actually come pre-installed on your devices that you actually can't remove. And loads of these applications actually contain vulnerabilities. And many security researchers actually target specifically these applications for this exact reason. I suppose me being one of them. Okay, so let's actually do that. So I'm going to be showing some demos of various OEM information disclosures. We're going to be looking at some information pilfering, some SQL injection, kicking it old school on Android, and the fact that there'll be no custom application development. Okay, so I've got a device connected at the moment. And if we go into the content provider section here, what I'm basically going to do here, or how I found these vulnerabilities, was just by issuing this command. So by filtering by all content providers that don't require any permission to read or write. And then basically going through each one of them and saying, okay, well, if I read from you, what kind of information are you giving me? Are you giving me passwords? Are you leaking instant messages? What is it? So it was just a process of going through each one of them and seeing exactly what it's leaking. So if we look at IM, which is an application that came on my device, it actually leaks instant messages. So if we query how content URIs are actually formed, so let's form one. I want to query a content URI with that authority. Okay, so on Android, basic content URIs look like that. It's got content, // and then the authority that you would like to query, and then some extra little path, which is not always there. So there we go. This is basically just a testing phone, but there's me speaking to my buddy, and this is from an unprivileged context. I'm reading from this application's database without any privileges. And I've got quite a couple of these. So. If you look at an application called Social Hub, it actually leaks your Facebook, all your social networking messages. So if we query this, you'll see I've got 2 accounts registered with Social Hub. I've got an email account, so a Yahoo account, and then just a Yahoo messaging account as well. So what I'm going to do here is, because this is obviously not the whole story, if you suspect that there's more content URIs in this application than just the authority, then there's a tool provided called Find URI. So let's actually run Find URI on Social Hub. And what this is basically doing now is it's going to the application's executable and basically running a Unix strings on it, and then a Unix grep. But this is all done in Java. So you'll see that it actually turns out to be quite fruitful, that it provides a list of content URIs that are being referenced in that binary. So we can go through some interesting ones here. There's one called accounts. So let's query that. Okay, cool. So there, again, it just gives me the accounts. We'll get onto more juicy stuff with this. No. Yeah, sure. Yes, that's actually another thing, is that the APK files you can read from an unprivileged context as well. I would say not, but that's how it is. Yeah, sure. So a piece of malware could actually just straight away get all internally on your phone without contacting out. Say, okay, cool. What I have available to me, what kind of content URIs can I read from, and just read from them directly, and build up a whole profile of pilfered information. So if you look at some other security researchers' work, Trevor Eckhart released last year in September an HTC loggers application, allowed any application with basically just the internet permission to get this whole list of permissions effectively. So if you look through that list of permissions, that's a little bit uncomfortable. Okay, if we look at some of my more serious findings within Social Hub as well, is I found that Social Hub, if you use it for your email and your instant messaging, it can actually leak your email address and your password for your email address, or the contents of your email as well, or your instant messages. And this could all be done from an unprivileged application once again. So let's actually look at that. So I'm just going to run this again to get a list of content URIs. Can sometimes be a little bit slow because it's running on the actual device itself. But okay, so if we look here at something like, let's read from this one, emails. I'll give you one guess what we're going to find in here. So cool, there's my emails in HTML. So someone could download row for row say, okay, cool, here's one email just from this person. It actually gives a whole bunch of information. Let's actually see, it pops out. Oh, there's quite a number of emails here. Okay, well, that's not important. The most interesting one is probably one called dbprefs. Okay, if we scroll up here, we'll see something called Z7 IAM client settings password string, and that's the password for this email account. And then same goes for instant messages. You can also read the instant messages out of Social Hub. Quite a cool vulnerability, probably one of my favorite ones, is that you can dump all SMSs on a device. And you can do this by using some old school SQL injection. So if we look at this, let's say we would just like to read directly from SMS. Obviously there's SMS and you require the read SMS permission, right? So let's try actually query that directly. Cool, so as expected we get a permission denial. But what happens if we look at authorities that are in the same package as the SMS database? So let's look for that. I'm filtering the information command by just that package. And so we see the SMS authority here, which requires read SMS. But if we look at something like this, it's part of the same package. It's called channels, and it doesn't require any permissions to read or write to. So that's already quite promising. Because if we query this, great, so we actually get a response. It's not much use. But how about we actually try some SQL injection? So I try ask for a column that doesn't exist in that content provider. And there, if I press enter, you see your classic SQL injection error message. You're trying to select a column that doesn't exist from that table. So at this point, it's fairly trivial. I'm not going to give a little lecture about SQL injection. I'm sure the majority of you are familiar with that. But how about if we just ask for SQLite master? So I'm saying, so effectively the command will be select star from SQLite master and dash dash, which then comments out the bit that is from my channels. And you'll see here that you basically get the whole SQLite master, and you can get the various tables that are present in this database. So what they basically did wrong here was they are sharing one database over multiple content providers. So the fact that you can inject into one content provider sort of brings down the whole team. I'm not going to scroll up. Basically, one of the tables names in here is called SMS. So what would you expect to happen now? Great. So there you go. Babe, you were awesome last night. And and whatever else is private to you. That's not private to me. Yeah, so credits to Mike Orty for finding that. He's a member of our labs team. And doesn't it kind of feel 2000-ish? Cool. So also there have been other OEM applications found by another researcher, our head of research, Nils. He actually found on one of the manufacturer's devices that you could turn a phone into a bugging device just by visiting a website. And how he actually went about this was he obviously had a WebKit vulnerability at hand, and then he noticed that the browser on this specific manufacturer's device always has the install packages permission. And basically from there, he used a WebKit vulnerability to install another package on the device. And then he also found that this specific manufacturer was exporting a service, a recording service, which allowed the recording from the microphone and then it basically allows you to dump it in a WAV file or something like that on the storage. And using these 3 steps, he could turn the phone into a bugging device just by visiting a website. So the chaining of vulnerabilities can cause potential amounts of damage. Another thing that I actually found on my device was that logs provider, so it pulls in pieces of information from various apps and actually logs it. So the same thing here, your SMSs are logged, your emails, your instant messages, and I even found that your call logs are in the logs as well. So you can get basically a very good profile of someone from reading this. So let's actually look at this. If I filter by logs, and in here I don't really have any clue what I would query here, because if I query just logs straight, it says unknown URL. So maybe we could use find URI to actually look for references inside the executable, and there you go, there's some pop up, and some obvious looking ones, your email, which I won't dump again, and then one called history S. I'm not sure about the spelling of that, but if you query that basically provides a complete overview of your logs. So there you go, there's phone numbers and SMSs, various emails coming in and whatever. And then something that's actually sort of half an OEM vulnerability and half an Android vulnerability is that you can read from the settings storage. So on my device, it was actually possible to read the settings secure content provider, and I could find the SSID and the WPA2 password of my portable Wi-Fi hotspot. So if we look at that here, I'm actually just going to query it directly. Settings secure, and there we go. So there's some information, and then if you actually, I don't think it's actually on this device, but if you put your SSID and password, it'll actually appear in this list as well. As well, I found more than 10 similar type vulnerabilities across many OEM apps. They're very easy to find. It's basically, they're sitting right at the surface. You can just do a couple of filters and read here and there and win. The impact of this is that an application with 0 granted permissions can get the following information: email address and password, email contents, SMS, instant messages, social networking, call logs, notes, current city, and portable Wi-Fi hotspot credentials, not to mention the fact that you could also read the contents of your SD card and upload it. And I'd say that that's a pretty decent profile of someone using a phone. That's pretty much all the sensitive information on the device. So if you look at why is this happening? Manufacturers commonly bypass built-in OS features. Sorry, I just want to take a sip. Cool. So they don't actually often set the correct permissions on the own applications that come with the devices. And I'm not sure if this is a lack of knowledge, maybe. It's a very new platform, so you can't use a lot of conventional programming wisdom when it comes to Android. You actually have to sit with the documentation and see what's new about it. Or maybe it's due to tight deadlines. Maybe the developers get pushed to say, look, we need a product by 3 months' time, make it happen. I'm not actually sure about that. So if we look at this from a malware perspective, you can build a very decent user profile from a completely unprivileged application. We saw that you can get installed package info, upload the entire SD card, pilfer from leaky content providers, and get device and platform information. And that's pretty much all the information that you need about a device and the owner of the device. Some useful binaries that a piece of malware could use are things like Toolbox. Toolbox comes on every Android device, and things like dumpsys. Dumpsys is actually supposed to be used in conjunction with the dump permission, but if you actually run it without having that permission, you can actually get a list of of email addresses on the device as well. And then things like BusyBox, which is your multi-purpose binary that's really awesome. If we use BusyBox here, you can use it from the Mercury shell, or not. Okay, let's just go into a shell. So you see here I've got BusyBox running, and you can get some really useful information out of BusyBox. Like let's do an ifconfig, or yes. Cool, so there's your internet connection, and if you connected to a wireless hotspot, your IP address will be here as well. If we look at some cooler things, some dirty tricks that malware could perhaps use, how about piping a shell to a remote computer on the internet? That's completely possible as long as you have the internet permission. So I'm going to be showing that. Just want to get into another shell here. Okay, basically I'm just going to be opening up a Netcat listener on the same device, but obviously that's because I don't have an internet connection here. But you can also pipe a shell to somewhere on the internet as well. Just bear that in mind. Cool. Maybe this is an opportunity to show off the modules section. So in the modules section here, it basically works in a very similar manner to Metasploit. You can write a new module for Mercury, put it in the correct folder, and then it becomes available for use within Mercury. And I've actually made a little one here for a reverse shell, using BusyBox, well, basically using Netcat and just piping an SH to somewhere. So if we run that, it tells you need those arguments. And I'm just going to point it to that Netcat listener on this one. So when you run that, there you go. There you've got your shell, which could be listening anywhere on the internet as well. It was also found that you can crash the log readers. So the log files are actually world writable. So you can go inject malformed data into the logs, and at that point logcat actually crashes. So you'll see that you can read up to that point in logcat, and anywhere after that is blank. You can't actually get anything from the logs. And the reason that this actually happened, I'll show you in the shell, is that it was dev log. Cool. So if you look here at the 4 different log files, you'll see why this is a problem. It's got world writable flag on it. So this actually causes logcat. So if you type adv logcat, it actually causes it to just bomb out with an out of memory error, which is also quite interesting. And then again, a malware could use techniques, get the latest fresh exploits. I've said multiple times that you can get a lot of information about the apps installed. Maybe even like that gentleman said, you could read the apps as well and perform attacks without even contacting a server on the internet. And basically exploit vulnerable apps for whatever your reason is. And again, the only permission required to do any of the attacks in this presentation is the internet permission. So it comes down to this. which application would you install? The piece of malware that is obviously malware, the once services that cost you money, your messages, or Mercury, which is basically just asking for internet permission. All applications on the marketplace, or a very large percentage of them, actually require the internet permission to display ads and for various other purposes. So that's not an uncommon. I would probably be caught out by something like this as well. So how do we fix this? Obviously, developers can't help Android vulnerabilities. You know, the inclusion of a root exploit in an app, you got owned fair and square, to be honest. But developers can actually make their own applications secure. You know, don't do silly things like allow other applications to read your content providers without any permissions. Things like that really limit the exposure of your apps on a device. Yeah, and you could use a tool like Mercury to actually look at the exposure of your app. So future plans for this, I'd actually like to make it a testing ground for exploits of all kind, not just application exploitation. Maybe some fuzzing modules and things like that for native code fuzzing, and maybe even turn it into a full exploitation suite. It's pretty much open-ended, and it would be cool to have the security community contribute and hear your ideas about it. So yeah, the obligatory, please fill in your feedback forms, and there you go. There's mwr.to/Mercury takes you to the labs website, MWR Labs, where you can download the tool and find, there's very sparse documentation on it at the moment. But also there's information there about the GitHub link, which you can go check it out and contribute if you'd like to. You can also follow for news and updates about Mercury. You can follow Droid HG. Cool. So any questions? Yeah?
Does Mercury run nicely in the emulator?
Yes, it actually runs really nicely. Emulator, yeah.
And did you write an exploit for Logcat?
For?
Did you write an exploit for Logcat?
For Logcat? No, that's actually not a module. Over the next couple of weeks, me personally, I'm going to be adding very many modules on the GitHub page.
This sounds so exploitable.
Cool. Any other questions? Sure.
You're saying any of the permissions to Google Wallet, the application?
Sorry, can you repeat that?
Google Wallet application?
Yes.
What sort of permissions? Does that allow reading files, etc.?
I'm not actually sure. I haven't actually looked at Google Wallet itself. But go ahead and look. You might be surprised. Cool. Thanks very much.